we'll be talking about optimizing performance of SDL systems. That's a paper we wrote with Michal Bulbuli, who couldn't be here today. So I will be presenting the work we have done. So just a few words to describe the technical context within which we are working and studying this performance aspect. So as you said, we are a tool editor, and we provide a tool that supports different languages. First SDL, TTCN3, and SDLRT. So I don't know if everybody is familiar with all these languages. I guess most of you are, because I know most of you. But just as a reminder, SDL models are seen, or at least in that study, considered to be an executable specification. So it's a model that is not only a static thing, but that contains, an action semantic and data types, an action language, so you can simulate, execute, and verify its behavior. TTCN3 is a testing notation, testing and test control notation, and it has the same abstraction level as SDL, so it's a perfect match to test an SDL specification. Okay, so if you look at the B cycle, you could see that SDL specifications are quite high on the left branch of the B cycle, and TTCN3 can be quite high on the right branch, even though it can also test implementation. Where the SDLRT is more design-oriented, it mixes model and code. So we won't talk about this. We will focus on SDL and TTCN in this talk. Okay. So why do you want to try to improve performance? Well, as you know, the systems are increasing in complexity. We have more and more distributed systems, like the Internet of Things and more M2M, autonomous drivings and everything. All these are autonomous systems that are communicating with each other. And the languages such as SDL can describe the functional aspect of the system you are working on, but not the non-functional one, like performance, typically. And because these autonomous systems have more and more features, we need to find the best way of organizing the allocation of these functional blocks on resources in the real world. Okay? But then, what we don't want to do is to have a performance model, which is not the real functional model. So we would like to keep the functional model we have, because that's the function we expect, and work on it to optimize the architecture. Okay? And same thing, when we talk about scenarios, we would like to use real scenarios, real-life scenarios. Okay? So if you look at SDL, SDL is perfect for describing functional behavior of the system, because you can execute it, you can run simulation, you also have tools that can do property matches, code generation, test generation, property verification, and so on. But there's nothing in the model about non-functional requirements, and especially time or energy. Both aspects people are fighting for today, time and energy. The SDL architecture is completely abstract. Okay, doesn't say where the block, the architectural block, will execute, on which resource, how fast, which energy consumption it will imply, and everything. And the same for the execution within the model. There's nothing about the time it will take for executing a transition or for going through a channel. We had this discussion this morning about IoT, not this afternoon actually, about IoT. There's no information about the time or energy it will take to go through a channel. So there's not enough information in the model. We need to add some information. So The functional model, the SDL functional model, looks like this. So most of you know it, but just to summarize, you have an architecture level with blocks, functional blocks, that can be made of sub-blocks. And when you are at the bottom level of the block, you describe the behavior with state machines that are called processes in SDL. And a state machine looks like this. This is a state, and that's the different inputs you can have. And when you have this input, you do these actions. So that's state, input, output, start a timer, go to the next state. When the timer goes off, it's like a message coming in. So that's timer T going off, and so on. And you have abstract data types. So you have the basic types, structured types, and you can have actions within the transitions. Okay, so that's the basic SDL model. You can simulate and verify its behavior is correct. When this is done, behavior is correct, you know it's correct. What we propose is to add some information to the model. So any symbol you have in the state machine, you can add some information to it. Okay, so you can say, for example, if I execute that symbol, it will take this amount of time, or it will take this amount of energy. So we have two aspects, time and energy. Okay, and I'll tell you the difference between the two. When we did the first use case with ST Microelectronics, they said, okay, that's interesting, but the energy we use depends on the load. So it depends on the input parameters, for example, you have from a message. So we need not only to say it will take 3 amount of time or 3 units of time, it needs to be 3 times something, you know, maybe the size of the message we receive. So we have added the possibility to actually put in the spend time, you can manipulate the information that is within the state machines. Okay, so you can just put 2 or 2 times y, for example, in that example. Okay, and you can do that for all the symbols. So in practice, you can have a very high level performance aspect where you just define time for one transition, one state, one input, or you can do it for each symbol, so that if you have decisions, you might have different execution times if you go to one branch or another. Okay. Then comes the question for the allocation. I said there's nothing in SDL that talks about allocation. So where do we run the blocks? That's the problem. Okay. So we didn't want to make up a new diagram, so we do use the UML deployment diagram and say, okay, we have the concept of nodes and components. We will use that and use you know, the added information to what you can add to the nodes and the components to make a multiplication factor to the information we have put in the model. So typically, this is node 1, node 2, so it's really execution nodes. And what we say here is that block 1, B1, runs on node 1. Okay? You have first the time when you execute the different symbols in the machine, but actually the time you put in the state machine cannot be compared to the time of the timers. You know, because very often the timers you have like now plus 5 and 5 unit of time. But if you say this symbol takes 5, it's obviously not 5 unit of that unit of time. It's something different. So you have a multiplying factor, in that case here, divided by 1,000. So if you have 5 for a symbol, it's 5 divided by 1,000 unit of time. You see what I mean? So that you can mix the timer factor and the execution symbol factor, okay? Because in the end, when we run the system with this information, we will take into account time advances, and eventually the timer will go off. Okay, this has to be taken into account, because maybe a scenario will go wrong because of that. And also we have 2 other things, is the transfer time. If you're on one node, and you send an information to another process on the same node, it will take a certain amount of time to send information internally, but if you send it to a remote node, it would take a different amount of time, maybe much longer time. Okay. Typical example would be if you have a dual core processor. Okay, so each node is a core. If you run on the same core, it's very quick to go from one to the other. But if you have to talk to the other core, it will take some more time. Also, another thing that is very important is the fact that time on two nodes run in parallel. So it does not add up. Okay, it's the max value. So if it takes 100 here and 80 here, in final it will take 100. Okay, where energy, we call it payload, but the term is not very good. Okay, the energy that will add up all the time. So if you have 100 here and 80 here, it will end up with 180. Yeah. Now the question is, okay, let's run the system with this timing information in it. Okay, which scenario do we want to use? We want to use the real scenarios, so we will use the real test cases. We have TTCN3 test cases. Let's run them against the model. Okay. In this approach, for the time being, executing the test is like running it on a different node, and this node is very default because it takes no time. Okay. So executing the test case in itself does not take time. We just will handle the time within the SDL system. Okay? But the good thing here is that we have a real functional model, SDL, and a real test case. Well, actually, we don't have one test case. We have a lot of test cases, because in TTCN3, we have a lot of test cases. Okay? And we will run the test cases against the model and take into consideration the time spent. So here is a small example. I don't know if you remember in the previous slides, we had put in information about the time it takes to go to a state, and we said 4, for example, divided by 1,000. So that's what you will get, 0.004 as the timing information. And as I said, if the time adds up when executing the system and the timer has to go off, well, the timer will go off and maybe the test will go wrong. Now, what we have done in the tool is, because you have a lot of test cases against one model, and you have different architecture, we wanted to build up a matrix of the result. So what we do actually automatically is that you define a set of architecture. So it's a deployment diagrams, basically. You have a monocore, dual core, quad core, and so on, maybe different machines, whatever, with different information, timing information. Maybe this core is going faster than this one, and so on and so on. So you list all the architecture you want to explore. Then you list all the test cases you want to execute on the system. Okay? And it will run all the test cases against all the architecture. So it's like running the simulation automatically. Remember, I said in the beginning, the model is right. We're not trying to verify the model. Right? Functionally correct. Now we're running it blind, okay, in the background, except that if the timing information that the test case is not right anymore because of the time consumption, it will say somewhere fail. So some cases might not work anymore because of this. Okay? So in that case, everything works, and you get the result for monocore, all the test cases here, balance, all the test cases, and so on. And we made a graphic where each color is an architecture. So the blue one is unbalanced. Can you read? More or less. This is unbalanced, the blue one. The green one is balanced, and the red one is monocore. And each branch here is a test case. So you can graphically see which architecture has the best result for which test case. Okay? This is a simple case where obviously the red one wins all the time, so no trade-off. But that's not the case in practice. Very often you have to make a trade-off, between some cases, test cases, scenarios, and some architecture. Some architecture will work better in some test cases, and the other way around. And you have here a small tab. This is the time information, and if you click on the tab next to it, you'll have the same representation like this, but for energy. Okay, so it's very synthetic representation of the results. Now we have been working and extending this on 2 use cases. I talked a bit about ST microelectronics, but I think it's interesting because ST microelectronics is making hardware, you know, processors really. But simulating VHDL, language they use for describing processors, is very time consuming, it's very complex, very complicated. From the architect's point of view, they want to use higher level descriptions, like what we have in SDL, add some information to it, and make the trade-off very early. And just do some verification with VHDL, but the trade-off, they want to make it before. So that's one use case. Another use case we have been working on is with Airbus Defence and Space. It's a satellite they will launch to Jupiter to observe one of the moons of Jupiter, and will send back the observation you know, from cameras and sensors down to Earth. And they also have a trade-off to make between all the sensors, because actually they have too much information to send. And the data link is very slow. So there's a lot of trade-off to do between how they handle the information, gather it, to give it priority or not, and so on. Because they have 2 links down to the Earth and so on. So there was 2 very interesting use cases about optimizing the performance, and we'll keep working on improving this starting from this. So as a conclusion, what we try to do is to keep, you know, the functional SDL model, because that's what people work on in the first place. Don't change them, you know, just add information to them. So functionally speaking, it won't change anything. Use the real test cases, real functional test cases with TTC and FRIP, and try to, you know, combine all this information and run and produce some graphical results that can help, you know, architects to find the best architecture in terms of time or performance in time or energy. Okay. That's